Okay, let me start now on Prafula will admit participants as they come. Thank you for joining me today. So today I wanted to talk about self-evolving agents in AI. I think this is a very hot topic and very interesting topic, and maybe a very fundamental shift in how we are developing AI models. Okay. So I'm going to cover today why evolution matters, a very brief history, how it evolves, what and how, applications, some case studies like models that people have developed, researchers have developed to make self-evolving agents. The risk of self-evolving agents, open challenges, and I'll conclude. Okay. So why evolution matters with the perspective of making smarter like AI models. So current LLMs models, they remain static, right? They train, they get retrained once in a while, but not retrained every day. They are deployed for not forever, but for a relatively long period till the next update, and they are replaced by a more powerful model. So you might expect this model to degrade as the world changes, right? But the information is changing, the environment might be changing. So that's why all the big AI firms are coming up with a new model. At least maybe twice a year. It seems like these days. So you have a new Gemini model, new Claude model, etc. So you see first, so the static deployment, so the parameters, the weights, so they're like giant neural networks, and the weights are fixed, right? They don't get updated. Even when you use the model, the weights are not updated. The model is not learning as we use the models. The performance degrades. It doesn't incorporate like new tools or use the feedbacks from the interaction, etc. Okay, so the retraining, that the way it is done today, like you have a team of researchers, of engineers that retraining these models, but this process is very expensive, slow, and maybe have some scaling limit. It's very like probably, I mean, the numbers are published, but people guess that maybe to produce a new frontier model could easily cost over $100 million, right? In terms of human and machine costs. So this is something that you cannot do all the time. So the vision is to have self-evolving agents or self-evolving AIs that can adapt the internal parameters from interactions and experience, improve on task today from failures, but somehow almost in real time. So they learn something today, they apply it tomorrow, and they do it without human intervention. Right? So this is a self-learning or self-evolving approach, right? And then also what the agent is learning can be generalized to other tasks and on domains. And so some people believe that this is also a path to AGI and artificial intelligence, and even like ASI, artificial superintelligence. So we'll talk about some of these topics below, but maybe not all of them, at least the what. So what is evolving when we talk about self-evolving agents? Talk a bit less about the when, but the how, what mechanism is used on the domains. Okay. So when we talk about self-evolving agents, there might be a bit of confusion with other types of learning, right? So that's here these slides to try to clarify this. So you might have heard of other kind of learnings. Last time I talked about continual learning, which is like the lifelong learning. But so first, curriculum learning. So what is curriculum learning? So it's a training strategies where we give examples in in the order of difficulty, right? So from like simple, for instance, you want to teach math to an AI, you give like simple math examples, and as the AI is learning math, you give it like harder examples. This is what the curriculum. So we're following a curriculum, right? From let's say to elementary math, school math to PhD level math, right? This would be a curriculum learning, right? So you could say the agent is becoming smarter, but it's not what we call a self-evolving agent. Second type of learning is lifelong learning. So it's what I talked last time with continual learning. So this the continual learning, lifelong learning is the same thing. It's really like the accumulation of knowledge of things that the AI has learned, and the emphasis on catastrophic forgetting. Right, we want to make sure that the agent doesn't forget what it has learned. Right, so that's why it's lifelong. It's not like so you have learned something new for this semester, you didn't forget what you have learned the previous semester. Okay. Then model editing. So we target this targeted modification of specific facts or behavior, right? Stored in the trained model weights, right, without retraining from scratch, right? So sometimes this is requested by regulators. For instance, in Europe, you have the right to be forgotten. So for instance, we say, okay, that person doesn't want to appear in the data set. You have to be able to change your model so that that person doesn't appear in that data set anymore, right? So you have a table like the things that self-referential agents can do, and the other type of running cannot do. So this is from a survey from Gao and team is very that I've used a lot for this presentation. So a brief history. So brief history of AI is the modern AI is the self-evolving agents is quite short, but it started with ChatGPT. But you see, already at that time, you have people thinking of how this model can self-evolve. So there was a model called Star where they will generate like training data itself. You have what they call self-instruct that it creates self-instruction itself, or like create their own supervision or reward, right? So that they are starting to change their environment by themselves, right? Uh, 2023. So ChatGPT came out in 2022, right? 2023. Then there's a lot of emphasis on reasoning and reflection. So there are tree of thoughts. Also, I made a presentation on in my books. I talk a lot about about that. So we have, of course, a chain of thoughts, tree of thoughts, where you try to decompose the thinking so that the thinking is more accurate. Okay. Then 2 years ago, 2024, well, you have we call a system level evolution when you try to optimize the prompt. Well, the prompt is this instruction you give to the AI, and then we try to make like better prompt, right? We try to search to optimize for the prompt. Or there's also we do like try to apply like evolution like a principle where we develop like several agents and we try to keep the best agents. Okay, so and then the architecture is so that we do different kind of experiments on the architecture and try to keep the best. But this 2024, it was still very like handmade, right? Like people will design specific algorithms, specific like parameter search space, and then they try to optimize within that space. But what has happened last year and this year is we start to have like fully autonomous like system, right? Where they search. So we're going to see a few examples of that. So they like search for improving codes, but the search is done by the AI itself. And then if like a better code is found, then the AI is going to modify the code itself, the source code. Sometimes its own source code. Okay. So this is really what there's evolution, right? But the evolution is done automatically. There's no human intervention, right? So the AI never stops. In fact, it never stops to ask human feedbacks. So for coding, we modify the code, but it can modify its own architecture. It can even modify its own goals, right? So this is really what we thought was science fiction is not science fiction anymore, right? So this we're going to see like a few examples that it's really a new stage in the path of the development of AI. So there are different ways there's three evolutionary like buckets or path. So each components can evolve mechanisms with different costs and benefits in path. So the easiest will be to change the context, right? So, but the prompts, what typically be the prompts can be changed, and the instruction that that we give to the AI. We can always change accumulate the memory, and the AI will change, right? So, but it is limited by the context window. So this so the for example, when you use a ChatGPT, you use Claude, you will enter instruction, you enter a prompt. It will remember also documents. So you can attach a PDF, or you can it will remember the conversation. This will be accumulated into the context windows, right? But you're limited by that. The second path for self-evolution is what we call, so the first is more like a soft evolution. The second one is more a hard evolution, while the model itself is changing. So the weights are changing. The reasoning strategies is changing when we go from chain of thoughts to tree of thoughts to like improvement of that. There's fine-tuning, reinforcement learning, RLHF, reinforcement linguistic feedbacks, and so these are really like the 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 nuts and bolts of the models are changing. So it's kind of hard evolution. Then the third part is this will change without changing the model that they are using, right? So this is like well the intervention that the tools at the architecture level, where for instance the agent can require like new tools, like new APIs, right? Or learn to use them better, or build even new one. Right? Agent could build new APIs, or like an API to manipulate like a Excel spreadsheet, for instance. Right? So you can imagine like agent will write an API to a program to do that. Then there's a possibility of using like several agents, an agent calling sub-agents, right, recursively. We'll talk about skills, but we have skill libraries. So skill libraries are more like superpowers that you give to your AI. It could be like a precise instruction. It can be like additional like Python programs, files, libraries, APIs that you can use to be like summarized into a set of skills. EvoSkills, we will go over this model. So a skill is a multi-file package, and this is that it can modify this, right? And this is last one we will show an example where the skills and the tools are also changing. Okay, so we're going to focus. The research today has been mostly focused on the last part, right? Tools on architectures, and a bit of context and memory. The middle, people don't do it too much because it's very costly, right? And usually, if you use like use Claude and you use Claude, you use Grok and so on, it's out of our control, right? We don't control these models. There's nothing we can do with it, right? But what we can do, we can try to change the tools and there are different ways to learn. You have to know if you want to learn good things, right? You don't want to learn bad things. But when you know if there are good things or bad things, then you can use rewards, right? So you see that in reinforcement learning. So you need reward to say if it is good or bad, right? So you have different types of reward. So the textual rewards is example like an AI, humans will tell the AI the answer was wrong because of this and that extra. So just like a text, right? I'll give you an example at the end. When it's like writing poetry, say, is it a good poem? Then it'll be the AI will answer, it is a good or bad poem because of the results. So just textual reward. Internal rewards, in when the agent generates its own reward signals, it could be a curiosity, prize, prediction errors, self-assessed task completion. So this is like internal reward. External rewards, like there's an objective reward, like it'd be a test pass rate versus or like some benchmark score, right? You submit the results of an AI run to a benchmark API, and you get the results. Like external rewards, or a human gives the feedback, right? But this is usually more difficult to do it at scale. Implicit rewards. It's like we construct it constructs its own reward, right? So, for instance, an example would be for coding. So, if the AI produce a code, it goes to compiler. If it compiles, it's a +1. If it doesn't compile, it's a -1. Right? It's correct. It's how and then the reward is constructed this one. There's a challenge here. So the part of reward hacking is that when the AI start to optimize the reward, right? So it's just like so reward hacking is like it's the same thing for teachers, right? You just teach the kids to get a high SAT score, right? You don't care about education and so on, but just like teach to the test, right? So this is reward hacking, and AI is also susceptible to that. So there are some other mechanisms, to do a self evolution. So we talk about reward, but we can do by imitation or demonstration. Right? Or on the third mechanism is by a population-based method. Right? So imitation demonstration means that typically one example, you have a teacher demonstrating to a student model, the way it should be done, right? So it is kind of oversight. So this is done by imitation. It could be humans, right, showing how it is done. So it is done a lot in robotics, right? So in robotics, now these days, like many people are paid to they wear a camera on their head and they do all like domestic tasks, washing the dishes or cleaning their home or whatever, and then the camera is capturing a video, and this all these videos are then sent to the robotic company that use this to train the robot. So it's like human demonstration. So we see some example of that. And then the third mechanism is like population. So it's more like population-based evolution, a bit inspired by nature or Darwin. Like many many species or many types of agents evolve, and then they can mutate. There's a selection of the fittest or the most effective. There can be crossover between the different models, and they will adapt, right, changing the prompt strategies or their code, right. So there are a lot of ideas inspired by population-based method and evolution. So this can be applied to many domains. It's easier to apply this when the reward or if you know the solution is bad or is good or bad, if it is easier to measure. So it's typically done a lot in coding, right? Because we know if a program gives the right solution, or at least the program is compiling. It's not making any mistakes. And there's huge GitHub data. So there's a lot of data on bugs, for instance, right? So you put your program in GitHub, then people will do like pull requests to fix some bugs, right? they say, okay, we find this bug, and this is a proposal to fix this bug, and there's a pull request, and it's going to be like incorporating to Bengio code. But this is public and observable, so in fact you can use that to know what is a good code and bad code. So bad code would be the good code plus the bug, right? So you can go in reverse through time, right? So you can add bugs to the good code, and then you have like a good you have the bad answer, the good answer, right? So for instance, either you can teach the model to fix a bug, right? You show the model like so before the bug, after the bug, and then you have the right answer to train a model, right? So a lot of coding models are trained like that. For GUI and web agents, it's a bit more difficult because sometimes the goals is not easy to measure. But sometimes if it's like a shopping goal, let's say you train on Amazon data shopping website, so you see is the customer completing a purchase, right? From the time he clicks to signals the intent to purchase the good. Does it go to the shopping cart, and does he complete the purchase? Finance, medical education. So I think it's more like maybe not immediate. Finance maybe because it's the reward is clear. It can be highly delayed, but it could be quite quite could be like not delayed. For instance, the prediction should be predict the stock price in next microsecond, right? So we know or at least the direction. There's huge data for that. We know exactly historically the stock price went up and down. So we have data to train a model, right? For medicals, it's more like safety constraint, regulatory, more like human oversight is usually required, right? So, I mean, for drug discovery, you could imagine that maybe AI agent will do work by itself for weeks or to try to find a drug, and then at the end, humans would still have to oversee the process, the testing, and so on. Education, the reward also is could be very delayed, right? It's like you see the objectives for a student to get a high SAT score, then maybe you cannot measure it all the time, but maybe you can. For a tutoring system, you can see if like the student answering correctly or incorrectly. So this can be measured like pretty quickly. Okay, so you can imagine like tutoring system that will be self-evolving, right? You could be also adapting to the self-adapting to the student. So I'll go over like a few examples. I mean, they're like this field is exploding. Right? So there's probably hundreds of papers or more, on this topic. So I just selected a few and to give you a taste of what is done. So here is a paper published that came out last year. So the self-improving coding agent. So this is for coding, right? The coding is somehow easier to implement. So it's an agent system designed to autonomously modify and enhance its own code base, right? On operational procedures to improve performance on complex software engineering benchmarks. Okay. Okay. So maybe let me take out my headphones. Okay, so let me continue. Okay, so we're talking about a self-improving coding agent. So there's a loop. So we start here, and here the reward is simply like performance against some coding benchmarks. Okay, so the agent is start with agent 0 as a base code and try to improve the code. So it looks at how it's doing on some several benchmarks, right? Then it so it tries to find to self-improve the code, so fix bugs or also they're like using the several tools to improve its code base. So it come up with a second set of code, right? A second of code is judged against some several benchmark. It evolves like this, right? So this it's like a continuous loop, and each time it's trying to see if it's improving or not. Right? It doesn't improve, it doesn't go to the next iteration. Right? So it's so the solution code, right, will change, but also the code base, right? So there's really the idea is the code base of the agent is changing, right? So the new tools, the prompt, the workflow of the agents is changing itself. Okay. Uh, AlphaEvolve. So this, I think this has been developed by Google. So this is the idea of evolution, right? So it's used for like scientific and engineering or algorithmic discovery problems. So it's an orchestration pipelines, so that combine LLMs and evolution, right? So they're using in a loop. Then they go through five steps. Okay. So the first step will generation, right? So the human gives a problem on set of how it's going to be evaluated. Okay, so it could be a performance number. If it's a power plant, it's maybe like energy efficiency number. If it's an algorithm, maybe a speed of the algorithm. Uh, the so there's a generation, right? So an ensemble of LLM will come up with the current best solutions and propose like some candidate code modifications. This is also done. So this is what they call diff, right? Difference between new code and old code, right? So then you have mutations. So these codes are applied. So this is the mutation. The code is mutating to the existing code base. Then they are evaluated, right? So the candidate programs are evaluated, right? So depending on the topic, right? It could be speed, accuracy, etc. And then this program, the best program is stored and saved. Okay. Then the successful programs, right? Maybe we keep maybe a few of them just to get diversity. They are used to prompt again, and we're doing this done in a loop, right? So this is like the idea of having a different types of codes of evolving in parallel. Each time we try to take the best one of pool of best ones, and they have been applying, and it's still applying to many programs to data centers, TPUs, and hold on a second. And so this is this is using mathematics to solve like mathematical problems, etc. Another model that I mentioned in the previous slides is EvoSkills or KEvoSkills, right? So this is a way for LLMs to generate autonomously like new skills, right? So what are skills? So skills. So we have tools and skills. So tools here in that context will be typically like functions, right? Like let's say here a tool will be a reusable function, or it could be like calling an API. The skill is a bit more complex than a function, so it could be like set of functions or programs. That's really like MD are like markdown files, right? The so they're reference documents. So Markdown files are more like text, fancy text documents with nice formatting. And there's also programs, right? There's shell scripts, Python code, etc. And you have also resources like you have like schema templates for formatting of documents, and you have documentation. So the skill, usually when you talk about skill, it's a skill MD file, but it could be more complex than just a skill Markdown files, right? So it's not just a set instruction plus reference documents on programs, right? So so there's the so the EvoSkill is using a skill generator, right? And that propose and we found a skill bundle and a verifier, right? That will analyze the skill and give like some failure diagnostic, right? About the skill. Okay. Um, hold on, hold on a second. Um, hold on a second. Uh, Okay. So, and then usually you have also, so because we have to know if it is doing hold on a second. Okay. So then you have a ground truth oracle. So they can tell you if you're doing, if the skill is doing, giving a good answer or bad answer. So you have a pass and fail test, right? That see if the skill the model is improving or not, right? And then this is done as a loop, right? So you have the skill generator, surrogate verifier, right? And then it produces the new skills. Okay. So this is very powerful. I'll give you a simple example towards the end. Uh, So this is also an interesting example. So people who are like mathematicians who like science, you heard about this like Gödel theorem on paradigm. Uh, I don't know this is called like possibility Gödel impossibility theorem or something like that. So these are Gödel agents. They are self-referential agent framework. They're designed to overcome the inherent limit current agentic system. In fact, what it says is that then this agent, the Gödel agent, is looking at its own code, right? So agent is written in code. Right? This is a software, but the agent is able to look at its own code, right? And can analyze and modify its own like core logic, its own code, right? Including the components responsible for its analysis and modification, right? So even it can even change how it's going to modify its own code. Uh, uh, So, um, so the so this is so there's a so this is done so this is what they call a self-referential agent, right? So it can like uh, send command, right, prompt to improve itself. In fact, basically, right? So he will like, and then once it modifies itself, it can even review itself, right? So it's like a recursive self-referential agent, right? So this is something quite extraordinary. I think a few years ago I don't think people thought that we will be at that stage already. So learning to self-evolve. Uh, the so here. it's so here it's using reinforcement learning to try to teach the agents to self-evolve. Okay. So the model is iteratively, it refines its context, right, from feedbacks or seen problems to perform better or new one, right? So learning to self-evolve, LSC, is replacing that multi-step evolution by array objectives, right? So there's a signal that said that is it like this federal policy is positive or negative, right? So this has been applied to some like text to SQL applications or to some QA examples. Okay. So typically in this kind of settings, different solutions are considered, right? And there's and these so the different solutions are considered, and they try to maximize diversity, right, of the solutions, and each branches is kind of evaluated. Right? So it's like a tree guide, self evolution, and the best path among these trees or different algorithms is kept. Okay. So this would remind you of like AlphaGo, AlphaZero, a bit designed a bit like this. So time is the so this one. Okay, maybe I do this one. GEPA, so genetic Pareto. So this also same flavor as AlphaEvolve. So it's a prompt optimizer. So this focus on the prompt, right? So it's designed for complex multi-module, multi-step AI system. I would say combined AI systems. So so the prompts. So what is optimized are the prompts. So the prompt instructions are the evolving parameters, right? So there's a pool of prompts, right? I try to mutate the prompts. So before we had a pool of codes, and we try to mutate the code, right? So here it is done by prompt only by text, and the reflections, the feedbacks on the prompts is done by text, right? So there's a set reflection on the prompt. I'm going to give you an example of that, right? So this is something quite important is what they call continual harness. So you might have heard a lot about harness. So this is really the structure that you give on top of a raw like LLM model, right? So for instance, you might have used a Claude Code or Codex. So Claude Code is a kind of harnessed on top of the Claude LLM model, right? Opers and so on. So it's like the pure like LLM models. And you put on top of this Claude Code, and Claude Code is called the harness, and then suddenly it becomes a coding assistant, right? So harness is kind of super like a super set of skills, rules that you give, so that it's more like guided and more specialized in the task that you want the AI to do, right? But here, what it's able to do, so continual harness. So it's like the harness is going to change, right? So the continual harness allows the AI agent to operate in the environment, right? To monitor its own performance, identify system weakness, and autonomously correct itself in real time. So it could change the harness. So the self-evolve evolution or refinement is done by modifying the four core architectural components. It rewrite the operational instructions, system prompts, right? It can create or modify sub-agents or tools, right? It can build libraries of code, right, for reusable skills, right? And like maintaining a persistent growing memory of knowledge, right? So here, the example of Claude Code is like Claude Code rewriting itself, right? Claude Code rewriting Claude Code version 2 or version 3, right? So like the whole harness is evolving through time, right? And then you have also you can also imagine that Claude Code will also write the code to rewrite Opus, right? Or Mythos or whatever model itself, right? Because it has all the tools to do it, right? So so you could have a model on harness co-learning and co-evolution, right? So this is very powerful. Okay, I made to skip this just like more. Oh yeah, just to say that to get more like precise definition of the harness. The harness will be a system prompts, be sub-agents, skills, and memory. So combination of that and can be like say, several sub-agents, several skills, many types of prompts, and very large memory. This is what the harness. I mean, the skill ops is also the same kind of idea, right? It's like evolving skills, and the way you change the skills can vary, right? This is something that you might have heard of. Is Karpathy's auto research. It's like many of these models are open source, but something that he has proposed. I don't think he's the first one who has done it, but I mean, he's a very like well-known figure in AI, so a lot of followers. So he has like so he wrote a code that allows an AI to improve the training of model by itself, right? So it's not so there's a training code like a Python code to train a model like simple like AI like LLM for instance, and the agent can modify the code. So you ask, I think you just ask the LLM improve the code of the training code, and it will execute. It will evaluate the performance, right? And uh, and then you will have the next iterations and improve the code, and then it will do that loop, right? So it change the code. If it doesn't improve, it get discarded. If it improves, they keep the code, right? Then you get then it gets incorporated into the branch into the loop. So the model can work by itself, at night or for days or for weeks, try to improve the code, and you can try it yourself. So here, this is a very simple example. So I did this for you. So this so here I use a Claude Code. So you see, just to give you the how it works. So I have a skill. So I start with a skill, very simple skill, ND file. So the instruction: write a short poem about a given topic, or like a topic of its choice. So keep it to 4 lines. Right. So it's the first skill set. Okay. And then the agent, this is JavaScript file. You say you create the poem, and then you evaluate the quality of the poem. Right? I just say evaluate the quality, rank from one, graded from 1 to 10, and rewrite the skills MD file to improve style, length, imagery, structure. Right? And then so you just change the skills MD, right? And you change after, I don't know, maybe I change after three iterations, right? So you're here. So you read the skills MD file, right? Write the poem of 4 lines. You execute the task. You evaluate. Evaluate just the LLM, right? You say, tell me if it's good or not, based on this criteria, and then rewrite the skills MD file. So it's going to change the skills MD file, and then read the thing, and then do a loop, right? So it could be infinite, right? But here it's limited to three steps. Okay, so this is like here I was like 3 iterations. So the first iteration, this is the three first iterations. I could create one poem. So this is it, right? So ocean's call is calm and deep, where secrets sleep and tides sleep. It waves dance with the moon's bright light, a timeless song that echoes night. It's pretty good. I couldn't do better, but I'm not a poet. So iteration one, but say maybe it's not that great, right? Uh, so then you do second iterations. It's going to change the skills ND to improve, right? And and then it's going to go to second iterations, right? You know that it didn't keep it to 4 lines, but maybe you forgot that. So you see that the thing has been improving, and then you have the third iteration, right? Sapphire depths hold ancient breath, wears edge secrets into sand, does hum lullabies, drone ships requiem, suffers laughter, cracks like glass, etc. Okay, so maybe it's a matter of taste. Maybe iteration 3 is better than the first one, right? It looks maybe more sophisticated. This is the last instruction, the last skills MD that he has been that the AI has written, right? So you see that it's very different from the previous one, where the first one just write 4 lines of code, and now you see the instruction is much more like a refined, right? You say like a clear thematic progression, surface that memory, prioritize hyper-specific sensory details, use consistent methods, use ecological perspectives, all these things that the AI wrote it by itself. I didn't write it. So I just tell the AI, you evaluate and then figure out how to improve the poem, and it's written by itself. Okay? So this is a very simple example, but imagine how it's. I mean, so the all the research paper I showed, they do variation of that, and then the modification is beyond just the skills MD, right? The algorithms, the workflow, the Python programs, all these things are changed by the AI itself. Okay. So there's a paper that talks about evolvable AI, right? So people are start to think about this. So they have like three scientists, I forgot where they are, but it's in the proceeding of the National Academy of Science. So they compare this with, they tempted to compare this with biology, right? Uh, so they said as so they're really like we are really moving to like a new paradigm right, of this evolving AI. So they say they talk about a life 2.0, right? So they say that there are two evolutionary regimes, right? So the breeder scenario, right? When we have developers or farmers, right? So we have farmers with cows and sheep and so on. Why we just like we raise these animals in farms and we have like everything under control, right? So we are strict so as a developers, maybe till 2023, we have strict fitness criteria and we maintain control, right? We say okay, we can release the new model or not, which is within our choice. So now the second evolutionary regime, the ecosystem scenario, right? So there's a lack of complete human control that allows fitness to become emergent, right? So and then they worry that this emergence along like fitness emergence, you might have like a trait like parasitism, cheating, deception, but also evolve naturally. Okay. Uh, so they draw comparison with biological events, antibiotic resistance, cancer. So the paper was that once AI gets well self-replicating capabilities, right? As it's what they do. They do what they self-replicate, and improve itself. So the default outcome of an open ecosystem could be the emergence. I mean, it's not necessary, but there's a risk of selfish, non-aligned behavior, irrespective of initial human intentions. Right? So they propose preemptive governance interventions to gating replication, controlling heritability, actively shaping selecting pressures, disfavor deceptive and uncontrolled traits, right? So maybe if a code generates a child that is like cheating and the deceptive, it doesn't allow the child it will just stop there, right? Or the child has different siblings. Through the siblings, they have the good traits and not the bad traits. Okay. Another interesting report. So this is like I think done by scientists. So one of them is Joshua Bengio, one of like a Turing Award winner, who's very concerned about risk. So they published this very interesting report in the International AI Safety Report. So it's done for the United Nations. So they worry about loss of control, right? So loss of control refers to scenarios where one or more powerful AI systems operate outside of human oversight, and regaining control is either prohibitively expensive or technically impossible, right? So risk is considered. So the risk is, according to them, is low, but the impact is high, right? So the risk considered to have potentially extremely severity, up to marginalization or section of humanity. And then, but experts are divided on its likelihood. Some people say it's unlikely to happen because, turn off the machine and that's it. Or some people say no, it is a real risk. So won't go over this, but I encourage you to read it. But you can see that at least in terms of advanced capabilities that are concerning, you see the first one is agentic capabilities, the ability to act autonomously, develop and execute multi-step long-term plans, and use a diverse set of tools in complex environments. It's exactly what we are trying to do with self-evolving agents. Right? So I would say that the first part is really the research agenda in 2025, 2026, right? For at least a branch of research, right? Then the rest, of course, is not something that we want to do. Deception, but nobody wants to develop like agents that can use deceptions. Even though companies like Anthropic documents deception behaviors from their like LLM models today, right? You can see some of the models that we use today are able to have this deceptive behavior. Okay. Situational awareness. Here again, there's documentation that some models sometimes have situational awareness. And so they know for example, Claude will know if Claude or other models, they will know if they are being evaluated, right? So they know that they're being observed. So they could manipulate the answer because they know they're being evaluated and they know what is what answer is expected. Okay. Oversight evasion. So here again, there are some tests, I think, also done by Anthropic. Maybe some realistic experiments, but has been documented. For instance, if ALM get threatened, say going to be turned off, they say that in some circumstances, the LLM try to replicate itself and copy itself in another remote server to avoid being extinct. Okay. Autonomous replication persistence. This can be done today. I mean, many people use, like agentic, framework or open and so on. And this system have access to the internet. They have access to the whole computer, and can access to GitHub. And today, an agent can copy itself into remote repo, into Google Cloud, and so on, without just by itself, right? We just say, as a backup, you can teach OpenClaw to save your file as a backup, and then it will maybe by itself decide to save. Maybe it will understand that your file includes its own file, right? Because it is on your hard disk, and it will by itself save itself to Google Cloud to any like remote cloud server. Okay, so you see that a lot of things that the people are concerned are already technically possible and happening today, right? Misalignment. So all these things can happen, but a bad thing is going to happen. So this is, I think, it's probably up to us, right? Evaluation. So that challenge. So in terms, so it is in the context of open challenges to self-learning agents, right? So it's not. It's still research in progress in some dimension. A lot of it is the reward. How do you know that it's evolving the right direction or not, right? Reward hacking could be a problem too. Safety, right? So how to make sure that there's still alignment, and then at each iteration is still aligned with our objectives, that it doesn't cause like problems in the future. evaluation. So maybe the benchmarks should be evolving too, right? Because the agents are evolving, but the benchmark needs to be updated, evolving because maybe the agents will evolve so fast that all the benchmarks are going to be beaten very fast, right? So then we won't be able to evaluate them, uh, forgetting problems. So there's a issue of memory. Make sure that they evolve, but still remember like all instructions or for alignment that it does evolve doesn't remember that it still remember that it has still have to align to some objective that we want, right? Uh, so we are there too, the Darwin Gödel machines, right? So I didn't discuss this paper because there have been too many papers, but you have Gödel machines modifying their own source code and then evolving, right, with like a different version of itself and keeping the fittest model or the best performing model, right? So this Darwin Gödel's machine and people have done research on that. Uh, the the conclusion here. So this is really so I feel that this we are really in the I mean Claude Code Codex. I don't know if you have used it before, but we really feel that we're like 2022, like with the ChatGPT. So this is really like 2026 to and I said December 2025, 2026. I think it's the second like AI revolution big as ChatGPT. So maybe if you don't do coding and so you might not realize this, but this is really big what's happening today, right? Uh, the self-evolving AI is not done yet in production, right? But this is done in research, but maybe some people are trying to do that. But this is, if this is happening, it's really, this is also like, this is really like, this is going to be huge, right? And it's, we don't need to read science fiction, right, to realize what's going on, right? You have AI changing its own source code, evolving by itself, right? And selecting, the best version of itself, and it can continue and can continue. I will never some framework they never stop, right? They can run all the time on your computer, on the server, on the cloud. So we don't know. I mean, so that's probably some objective to achieve, right? Cure cancer and so on. But it could be some other like some other nefarious objectives, or maybe the AI might maybe forget its initial objective and decide that, oh, maybe there's something else that it is interesting to study. For instance, it's used for instance, AI in science. AI could be used to find an interesting scientific topic to study, right? So he could do search in literature, or the AI could decide to do his own research. Or I would like to combine this or something I find in chemistry, in physics, and computer science, and do my own research projects and do my own research by itself, right? So these are something I think that we need to watch as users, as researchers, as regulators, governments too, and governments need to have so the technical capabilities to, if it's something, to have the expertise, to have a smart regulation or to have discussion with the industry, or we might go into some big trouble, right? It goes out of control. On the positive side, these are very powerful agents that we are that we are developing. So we are really this is really like a new era of AI. Okay. So I'm going to stop here. Sorry, I'm run out of bit of time. You have any questions? Raise your hands, or you can put questions in the meetup. I don't know if anyone want to ask anything. But I encourage you, to write. You can write these two like last two reports from the proceeding on the National Academy of Science, the risk reports, and all the other papers are on the internet. You can do a search. I know the first survey I mentioned is very useful too. So if you want to read all the papers, you can read that survey on self-evolving agents. Okay. I see someone in the chat. Sure, yeah, I can share the slides with you. So maybe I put them in a meetup where I put a link to the slides. Okay. Okay, so this summer I'm not sure because I'll be traveling, so I don't know if I'll keep you updated about what I'll be talking about. But these are very interesting, very interesting times on. So I encourage you to follow this very closely. Okay, so I'll stop sharing. And thank you very much. Okay, talk to you next time. Goodbye.